Hello, everybody. Let's not waste any time with our HR diagrams and put them to work for us, the astronomer, so we can get some very useful things. What we're going to do now is we're going to take everything that we've learned about the HR diagram that's connecting properties of the stars, like the spectral class or temperature, to the luminosity or the absolute magnitude, and we're going to flip things around a little bit, and we're going to use our knowledge of the HR diagram to develop a new method to determine the distances to the stars that allows us to determine distances well past what we can do with just normal stellar parallax. So the name of this ends up with being one of the worst misnomers in all of astronomy. So the method that we're about to talk about is called spectroscopic parallax. I really don't like this name. I think it should be called spectroscopic distance or the spectroscopic distance method, but I don't know who came up with this, but they came up with an awful name and it stuck. So now we're stuck with this misnomer. So even though this is called spectroscopic parallax, it has nothing to do with parallax. In fact, the entire point of this method is to not use parallax. Yet for some reason, I guess because people were the strong association to parallax is a measurement of distance or can be used for distance, that it's a stand-in for distance. So not to be confused with stellar parallax, whenever you look at something from two different vantage points, different eyes, and you see how it shifts back and forth when you see it from two different vantage points, and that connects to the distance, and that's how we're determining the distances to the stars. That is stellar parallax. This method of distance is different. But let's just go ahead and dive right in and not worry about the misnomer too much, although it does rankle me a good bit. All right, so as I said, we're going to make the HR diagrams work for us. We spent a good bit of time establishing, say, this main sequence where 90% of the stars live. And we have this nice correlation, this nice connection between the temperature, or really the spectral class of the star, either one works, and then the luminosity of the star. And since everything's nice and constrained to this nice diagonal, all of a sudden, this is going to give us something pretty powerful. So let's say we go out to our telescope, we pick a star in the sky, and it has the telescope has a spectrometer on it. So we take a spectrum of the star, we look at its absorption lines, the details of it, to determine its spectral class is an A7 star. Now, we know where this star falls on the x-axis. It's an A7 star. We know what temperature that corresponds with. Odds are this is a main sequence star because 90% of all stars are main sequence stars. So we can use our HR diagram, just go up to the main sequence. That's where this is where A7s would be. And now we can use our knowledge of the HR diagram, the fact that we understand this main sequence and this is this diagonal across the HR diagram to just read off the luminosity. So a luminosity of, 10.6 times the luminosity of the sun, 10.6 solar luminosities. Notice we just got to the true brightness, the absolute brightness of the star, its luminosity, equivalently its absolute magnitude. We never had to know the distance to the star to do that. We just had to apply our knowledge of the HR diagram. We just cheated a little bit, or rather we were clever, and we used the fact that we were able to build an HR diagram from being able to measure the distances to the stars, which then allowed us, if we knew the distance to the star and we can measure its apparent brightness, its apparent magnitude, then previously we used that to calculate the absolute magnitude, which we translated to a luminosity. So we did all this work of using stellar parallax to actually determine the luminosities of the stars, which allowed us to construct an HR diagram. And now we can flip things on their head, and have the HR diagram do the work for us. Because now we have the luminosity of this A7 star. We know its absolute magnitude. We have that we can exploit, or we can leverage, I don't like to use that word, we can leverage that we have this connection between our spectral classes, our temperature, and the luminosity of the stars. And what we're going to do is we're going to use this to determine a new way to determine the distances to the stars with only a couple of telescopic measurements. Go out, pick a star in the sky and do a photometric measurement. Just measure how bright the star is to determine its apparent magnitude. You can then use a spectrometer, measure the spectrum of that star. That tells us its spectral class, which tells us where it is here on the x-axis. And then we can read off the luminosity, or equivalent, we could read off the absolute magnitude. So we can take the spectral class and then use our knowledge of the HR diagram to determine the absolute magnitude, capital M. Now we know apparent magnitude, little m. We know absolute magnitude, big M. We know the distance modulus, apparent minus absolute magnitude, which leaves the only thing that we don't know in this equation is the distance. So we could solve for the distance. And therefore, we get the distance to the star without ever having to measure a stellar parallax measurement. A new method determined distance. Sure, this is a little bit of a runaround to get there, and it's going to not have flaws. We're about to get into some of the challenges this one has, but it gets around the major limitation of stellar parallax. Remember, measuring parallax to stars is very difficult. The farther a star is away, the smaller the parallax is. To the point that even with our most sophisticated piece of equipment that we've ever created, the Gaia satellite, whose entire purpose is to measure stellar parallax to new levels that we've never been able to before, it can measure stellar parallax to about 10,000 to 50,000 light years. By the time you're hitting the 50,000 light years, though, the errors are getting pretty large, so that you don't really have a very reliable distance measurement there. You might be thinking, that's a huge distance, though. 50,000 light years? But that doesn't even get us halfway across our galaxy. That doesn't get us to our nearing our neighboring galaxies. That definitely doesn't give us to the Andromeda galaxy, which is 2.5 million light years away. How do we determine those distances? How do we determine distances when it's physically impossible, based on the technology we have, to determine the stellar parallax? Oh, look at this beautiful method right here. Fantastic. As long as you can measure the apparent magnitude and take a spectrum of the star, you can use this method that we call spectroscopic parallax to determine the distances to the stars. But it's not without its flaws. So spectroscopic parallax here has a couple of issues, and they become pretty apparent pretty quickly. So here's a real HR diagram with the Hipparcos data. So let's go ahead and deal with this first part. So let's imagine we have a K0 star here. Notice that, should I read the luminosity off of the bottom or the top? The main sequence isn't infinitely thin. It's got some width. A K0 star has a range of luminosities that can still be a K0 star. There's a little bit of natural variation going on there. So do I read off, say, the bottom and get something like 0.05 or 0.05 solar luminosities, or I read off the top and get something like 0.5 solar luminosities? That's a pretty big difference. That's a factor of 10 different. So this width that the main sequence has, this natural width, translates to a large amount of uncertainty in the distance. As you can imagine, putting, say, a number that has a factor of 10 different here, well, do that in magnitudes, but that could lead to, if you change this number, you're going to change this number, and that can lead to errors of up to 25% uncertainty in distance. That's like saying that star is somewhere between 7.5 and 12.5 light years away. That's not a very good measurement. 25% error is not something to be proud of. However, we can leverage more knowledge about the stars to narrow that down, that we can understand why the main sequence has width and correct for that. So we can really beat this error down, but it's still there. We're going to take some error in our distance measurement using this method. But that's only the beginning of the problems. A bigger problem that we're going to really have to come up with is, what about K0 stars, we could go ahead and do our best measurement of here, reading a main sequence K0 star. Say we get 0.1 times the luminosity of the sun. But these are K0 stars up here as well, but they're also red giants that have, say, 100 times the luminosity of the sun. That's a factor of 1,000 difference in luminosity. Which one am I supposed to use whenever I use the spectroscopic parallax? I'm going to get vastly different answers. So which one do I use? What luminosity is the right luminosity to choose? The safe bet is that you're probably dealing with a main sequence star because 90% of them are all main sequence and only 1% of them are red giants. I like those odds, but not good enough for science. So how do we decide which luminosity we're going to use? The 0.1 luminosities for this K0 star or 100 luminosities for this solar luminosities for this K0 star? And here we have to be extraordinarily clever. We have to go to the spectrum and do some spectral analysis. Remember that there were details buried in the widths of these spectral lines. So if we go back to our spectroscopy that we covered a few weeks ago, then you remember that one of the things is that the widths of those lines, how wide, say, our hydrogen gamma or our hydrogen delta or our hydrogen beta line is, depends on things like temperature. It also depended on collisions, how often things were colliding, which was a measure of pressure and density. So the width of these lines depends on the pressure and density, which means that we can leverage this information and some physics to figure out which one of these two stars right here is the giant star and which one's the small star, the not giant star. How can we do that? Well, if you have a star with wider lines means that you must have a higher pressure scenario. We'll get to why it has a higher pressure scenario now. But a wider line is a higher pressure scenario. So the photosphere has a higher pressure. All the gas is at a higher pressure. So this one would be our smaller star. The wider the lines, the smaller the star. And conversely, the narrower the line, that means that it's very low pressure because it doesn't have a whole lot of pressure broadening. It has very little pressure broadening. So it's at low pressure. So the low pressure stars end up being our biggest stars. Why is that though? I mean, this is a nice mapping, but this seems like I just told you something without explaining it. That low density gives us narrow lines. So we go look for the narrow lines. We go, hey, that's the big one. And then we go look for the one that has the wide lines and go, hey, that's the smaller star. Well, larger stars, they're all puffed out. They don't have that much difference in mass. The mass difference is pretty small, but the size difference is huge. Hundreds of times bigger in the case of, say, a main sequence versus a giant star. So it's really, really puffed out, which means that it has low surface gravity, that means that gravity is not pulling very hard on the material in the photosphere, which allows that material to stretch out and be low pressure. So low surface gravity means the photosphere is less compressed and therefore lower density. Lower density, lower pressure. Oh, lower pressure, then that means that you'll have less pressure broadening, you'll have narrower spectral lines. Smaller stars, and roughly about the same mass, so take that same star and squeeze it down, it's going to have high surface gravity, which means that photosphere is going to get compressed, and therefore it's going to be at higher density and higher pressure. Higher pressure means more pressure broadening, means wider lines. So we can look at the widths of the lines to tell which stars are the big ones and which ones are the small ones. We can use the widths of the lines themselves and know that the width depends on this pressure broadening that we mentioned back in spectroscopy. to pick our giant stars from our main sequence stars. And yeah, it works. So let's take another example just to show you. So these are all F0 stars. So you have the same suite of spectral lines. You would come through and you would classify this as an F0 star. But now let's look at the hydrogen gamma line. It's nice and broad, and then it's narrower. And here it's very narrow. Same, look at these calcium lines, wide, less wide, narrow. So the wider means more pressure broadening, higher pressure, smaller star. This is our smallest of the three stars. This one has the narrowest lines, the lowest pressure broadening. So it's going to have the lowest pressure, the lowest density. It's going to be the most spread out. It's going to be the largest star. And then the one in the middle is the one in the middle. So what we can do is we can use this knowledge of the widths of the lines and our knowledge of the HR diagram to start looking at, hey, let's look at the fine detail of how these stars cluster and bring in some additional information of the widths of those lines, which allows us to create what we call the luminosity classes. So we have our spectral classes, our O, B, A, F, G, K, and M. But now we also have luminosity classes that are going to be determined by the widths of the line. The luminosity classes tell us how big the star is. You have the same temperature because you have the same spectral class. But then as you go to larger and larger stars, that means you're going to be brighter and brighter and brighter. You have more surface area to emit. So you have a larger luminosity. So our luminosity classes are really telling us something about the size of the stars themselves. And we can determine the size of the stars by the widths of the spectral lines. Now, by no means am I going to be having you actually look at spectra to determine these. I just need you to understand the concept. Because what it does is, hey, we can go look at the widths of the spectral lines to determine whether it's going to be, say, a supergiant or a main sequence star, or a subgiant, or a giant, or a bright giant. And we can then figure out, oh, well, we know how to read the luminosity off now because, say, it's going to be a star that's here when we know it's a giant star, so we should go up here to read the luminosity off. And we come up with 5 broad categories of luminosity classes. And these 5 broad classes, we actually subdivide ones. So our luminosity class, and we use Roman numerals for these. Roman numeral class 1 is for supergiants, but because of some recent discoveries of really bright supergiants, we didn't want to call them super duper giants or uber giants or hyper giants, although hyper giants is a term that we did eventually adopt. We call that luminosity class bright supergiants because, you know, they're more luminous, so they're brighter. And we have our supergiants. Luminosity class 2 are our bright giants. Luminosity class Roman numeral 3, III, are our giants. Luminosity class 4, Roman numeral for 4, IV, is subgiants. And luminosity class V, so the 5th luminosity class, are our main sequence stars. And we have this cartoon graphic that's right here just to show you that, hey, yeah, we have most of our luminosity class, say, main sequence 1s, V, fall along the main sequence, so we know how to read off the luminosity using the main sequence. If it has a luminosity class of subgiant, then we know, oh, if you're a K subgiant, go up, and you know where to read off, what luminosity to choose. If, let's say, we have another one, and it's a K giant, not a luminosity class 3, not a 4, then we know, nope, it's not a luminosity class 5, it's not main sequence, it's not a subgiant, it's a giant. We know to read off this luminosity. Clever, quite clever. Let me give you some examples. So because now we can give a full classification of a star, a spectral class plus a luminosity class. So let's start with the sun. The sun is a main sequence star. It's fusing hydrogen into helium in its core. It's in the prime of its life. So the sun is on the main sequence at 5800 Kelvin and a luminosity of 1 solar luminosity. It is a main sequence star, so it's going to get the luminosity class of V, and its spectral class is G2. So the full classification of the sun is a G2V star, or a G25 star if you want to say it that way. And that tells me it's a G2 main sequence star. We can take Rigel, pops up here into the supergiant. Actually, I believe that would be a bright supergiant. And Rigel has a full classification of B8 1A. It is a B8 blue bright supergiant. We can do another example, Betelgeuse. Betelgeuse. So we could go out there and measure the spectrum, see that Betelgeuse has incredibly narrow spectral lines. Therefore, it has an incredibly large size, low surface gravity, low pressure. So very little pressure broadening. So we can determine that it is a bright supergiant, a 1A luminosity class. What lines are there? We can determine that it's an M-class star, lots of titanium oxide molecular lines in that spectrum. And we can determine it's an M2 1A. It's a M2 red bright supergiant. And then we could have another star, Arcturus, a bright star in the sky, measure its spectral lines. It's kind of wide but narrower than main sequence stars. Careful analysis tells us that that width corresponds to a giant star, a luminosity class of 3. Its spectrum, what lines are there, and the strength of the lines tell us it's a K2 star. So we have the spectral class K2, luminosity class 3. It's a K2 3 star, a K2 red giant star. And finally, a summary slide. This is in the notes. I just wanted you to see this method laid out of how spectroscopic parallax works. Go to the telescope, do a photometric measurement, measure the apparent magnitude, photometry. Turn on your spectrometer, measure the spectrum of the star to determine its spectral class, leverage your knowledge of the HR diagram, and also leverage your knowledge of look at the widths of those lines to determine the luminosity class. So now you know which, not only a spectral class, but what luminosity, so how high up on the HR diagram do you go? That allows you to read the luminosity off the HR diagram. And now that you have the luminosity is the absolute magnitude. So you have determined the apparent magnitude, the absolute magnitude, solve for the distance, done. And this can work for stars that are more than 50,000 light years away from the Earth. Awesome. The HR diagram is working for us, and it's working pretty hard. All right, so I hope you enjoyed seeing the cleverness of how we can use the HR diagram to turn things around and make the HR diagram into a tool to measure distances to the stars.